Yeah, once again, welcome you all for the lecture series of digital signal processing. The connection. In the previous class, we studied about the Butterworth filter approximation method, the derivation part, and later on we solved two of the examples, like how to find out the order of the filter and what is the exact meaning of order of the filter and how to determine the 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 value of n when the low pass attenuation band pass sorry what is it pass band attenuation and stop band attenuation followed by stop band frequency and pass band frequency were given. Now today in this lecture, uh, last class I had given you one small example for homework. So I think no one has attempted it. I didn't receive any the any of the students solving that example and putting it in my WhatsApp. So only one student by name Chaitra, she tried the example and she posted her answer in the WhatsApp group. Not in the group. Like she asked whether the problem is correct or wrong through by messaging personally. I don't find any of the students have tried it off. I keep on repeating you unless you solve these examples on your own. So it will be very difficult, guys. In the meanwhile, you are supposed to cover the lab sessions parallelly. So that is one more pending job. So I thought of finishing this chapter. Then once again, I'll concentrate. I'll take a series of lab sessions as in the afternoon itself. That probably it may take some time. So let you all guys finish off your second internals. Then we'll see to that. Okay. Without wasting much time, we'll look into the problem. Yesterday's problem that where we left. I think this was the problem that we were solving in the last class, right? So this was the example I had given you for assignment. So let us solve this uh, example once again. What is the value of n here? Can anybody tell me the value of n? What you got? What is the n? So therefore, I think you had applied the formula. So n is equal to log to the base 10. So 10 to the power of minus 0.1 AP minus 1 whole divided by 10 to the power of minus zero point 0.1 AS minus 1, and entire thing is divided by 2 times of log to the base 10 omega p by omega s. Stop that. Now what is the value of n here? Quick, what's the value of n, guys? Can you able to see my screen?
Sir, we are putting it in the chat box, sir.
No, can you able to see my screen? Share.
Yes, sir, it's visible.
Okay. Okay. Okay, that the answer is 4, and most of you have solved this. Now we will move on to the next concept to find out or to determine the poles of this particular equation, right? So how now the second part is to identify the poles. Okay, now to identify the poles, in one of the class we derived an equation for finding out the poles, that is Sk is equal to cutoff frequency omega c and followed by what is the equation here, Sk into e to the power of into e to the power of j pi, right, j pi by 2n. Okay, j pi by 2n into n plus 1 plus 2 times k. So this is my formula to find out the k, the poles where k lies from 0 to, so that is nothing but 0 less than k less than n minus 1, which means that the value of n is 4. So therefore you will going to get 0 to 3 values. So therefore let me take k and sk value. So putting k equal to 0, k equal to 1 and k equal to 2 and k equal to 3. So for these many values I am supposed to obtain the equivalent pole values, right? Now first value s of 0, so first pole, that is omega c. Later we will see about the omega c, it is nothing but angular frequency. So I'll just take that e to the power of j 2 pi into what is the value of n here, in this case 4, into n is again 4 plus 1 plus 2 into 0, it remains 0. What's the answer here? E to the power of j pi by 8 into 4 plus 1 is 5. So therefore the first pole lies at e to the power of j 5 pi by 8, right? This is my first pole. Similarly, find out the value of pole at k equal to 1, s1. quick Quickly give me the answers for S1, S2 and S3. So if I put S1 k equal to 1, so what is the answer? So that is e to the power of j pi by 2 into 4 into 4 plus 1 plus k is 1 into 2, that is 2, right? So this comes to be e to the power of j pi divided by 8 into 4 plus 1 is 5, 5 plus 2 is 7, so that is 7 pi by 8, right? Is it not? So the second pole lies at e to the power of j 7 pi by 8 is the second pole existence. What about S2 and S3? So definitely these two must be the conjugate of these two. That is S0 and S1, right? So this will be conjugate of this. So let me know the conjugate of this. Don't say it is minus. It will be having some angle. Calculate and let me know. Later on I will tell you how it is going to be conjugate. E to the power of j, and it is also e to the power of j. Quickly, come on guys. Let me know the value of pole when k equal to 2 and k equal to 3. It is 9 pi by 8, right? Okay, good. So one is at 9 pi by 8 and another one is 11 pi by 8. Okay. So 1 over is at 11 pi by 8. Now this is the identification of poles, right? I need to plot this on how? S plane. See, S, when I say that S plane, so I need to map e to the power of what? J theta, right? How do you map the e to the power of j theta? It is nothing but what is this theta? Theta is nothing but a angles that is going to be represented in terms of what? Either in terms of either in terms of degrees or in terms of radians, right? So here 7 pi by 8 and 9 pi by 8, 11 pi by 8 are all in terms of radians. So you need to understand like what, how, where actually the pole exists. So right, so let me take a new value here. So this is my S plane. So this is my S plane. This is imaginary axis and this is a real axis. Okay. So now the first pole exists at S0 where it is existing. S0 is e to the power of j pi 5 pi by 8. So it is nothing but I just take it as 5 pi by 8. So what is 5 pi by 8? Where it lies? So it is nothing but let me convert this to degree so that it will be very easy for me. If I want to convert this into degree, that is 180 divided by pi, pi and pi get cancels. What is the degree that we're going to get here? Quickly, how much degree? In terms of degree, tell me. Tell me the value in terms of degree. So it is 112.5. So where the pole lies, so which means your angular frequency should from here I should measure. I'll keep a protractor and somewhere else. So this is giving me a 90 degree and here it is 180 degree, right? This is pi by 2 and this is pi. So in between this the value of 112 will going to lie, right? So somewhere else can I consider here? So somewhere else my first pole lies. Okay, if I measure from here to here, so this value is somewhere else 5 pi by 8 value or degrees, that is equal to 102.5 degrees I'm going to get. Now here I will mark my first pole, that is S0. Okay, is this clear? Now the similarly S1 is existing at 7 pi by 8. What is its equivalent value? 7 pi by 8. So where it appears to be, where it appears to be 7 pi by 8. 7 pi by 8, so it is somewhere else 157. Okay, 157 means, so again here, so it is 180 157. Here we are taking it as 112. So after this, soon after this, let me mark here. So this is my S1, right? Okay, now similarly S2 S2 will be complex conjugate of S1 and S0 will be complex conjugate of S3 will be complex conjugate of this one. Now why I am telling you it is a complex conjugate, just write these two values, which is that cos of so first value is e to the power of 5 j 5 pi by 8. I am telling that this is equal to this is equal to s naught, right? So this is equal to s naught. What I am trying to say is s naught and s3 will be complex conjugate. So s3 value is e to the power of 11 pi by 8. So this is equal to e to the power of j times 11 pi by 8. So put this in terms of complex cos and sin theta value, that is cos pi by 8 minus, sorry, plus j sin pi by 8. Okay, 5 pi by 8. So check this answer, how much it will going to get. Check this, and followed by you also take cos of 11 pi by 8 plus j times sin of 11 pi by 8. Check these two answers and see to that these two are complex conjugate or not. What is the value? Verify this and tell me the answer. What is the answer for cos 5 pi by 8 plus j times sin 5 pi by 8? See, you need to put your calculators in radian mode. Then only we'll going to get answer because 5 pi by 8 is expressed in terms of radians, not in terms of degrees. Okay. So you need to be careful in this in order to understand these problems. So what is the answer? Quick. So look at this. We solved for, I just repeat this, or if you have any doubts please go through this. So we have solved for the s0, s1, s2 and s3. Later on we got the value in terms of radians. I just converted that radians into the complex form, so you will going to get this complex form. So put these values in the s plane, so now you can easily map it onto the s plane, or else the other way, best way is you will be getting the values in terms of radians converted into degrees as shown in the previous slide, or so now and map this onto the s plane. So where you will going to get 5 pi by 8, that is nothing but 102.5 degree. So from the origin, from this place, I'll keep a protractor and I'll see to that where 102.5 degree appears. So this appears somewhere else here, so that is value of my s naught. So similarly s1 is 7 pi by 8, so similarly you go for converting into degree, so that is the value of s1 and the pole lies here. Similarly for s2 and s3. So since if you observe carefully, if you convert this value into complex form, so s0 is complex conjugate of S3 will be a complex conjugate of S1 and S2 will be complex conjugate of my S1 value. So this you can observe when you convert this value into complex conjugate value in the form of A plus IB. So I showed in the figure both the mapping. So that is S plane using e to the power of j theta and converting that in the form of a plus ib form. So both will be one or the same here. Okay, and here I wrote this omega c. Omega c is nothing but my radius. How do you calculate the radius? So radius is nothing but angular frequency. In one of the derivation, we derived the value for omega c also. So that is omega p divided by 10 to the power of minus zero point 0.1 ap minus 1 whole to the power of 1 by 2n. So apply this, you will going to get h of z value. Sorry, omega c value in terms of hertz. Now, once again, what is to be identified? H of S. H of S is nothing but my transfer function. So, since it is a all pass filter, so it no zeros in the numerator. Therefore, 1 divided by. So, this is pi k is to 0 n minus 1 s minus sk. So, this is my standard formula to write the any of the transfer functions here, right? So, if I since k value is running from 0 to n minus 1, the n we got it as 4, therefore 4 poles exist in the denominator, that is s minus s naught, s minus s1, s minus s2, s minus s3, the 4 poles. Now s0, s1, s2, s3 are already identified. Just substitute those values here. That will complete my the writing of the transfer function for the given specification. And one more very important point: if you observe the s plane, where the pole lies, where the poles lies, the poles is lying on left half side or left hand side of the s plane, left hand side of my s plane. Therefore what can I conclude that here? So this system, whatever you have developed an analog FIR filter, This filter is a stable filter, right? So what is the indication of falling of your falling of the poles on the left hand side? The poles are stable, our system is totally stable. So which means, given a specification, what is that specification? Oh, here it is specification. If I draw it, so this is my specification, right? So you have designed a filter now for these specifications. So that is, so where my passband frequency omega p was at 500 pi radians. So and the stop band frequency was at 5000 pi radians, and its corresponding value is minus 75 dB, and here the attenuation for passband was minus 2 dB. Okay, so this is h of j omega magnitude in terms of dB. So this is my frequency for this output. That is what I told you. Whenever I want to design a system, I will be having a output. This is my required output. For this required output, my input is, these are my input. What are the ap, as, omega p, omega s are my inputs. So for these inputs, I am trying to derive an system function like this. Later on, in Ascendus, you also studied how to generate the hardware for this. That is cascading of these transfer functions. What do you mean by that? What's the meaning of that? Which means that how to put in the form of hardware. Now, because you need hardware, right, to implement this equation, I have this equation, I need to implement an hardware. Once I implement that hardware will go into perform a job of this particular operation, that is low pass filter operations, right? So this is all about design of the low pass filter using Butterworth filter. Any doubts here? Let me stop. If we have any doubts, let me clarify and I'll move further. Now, I'll give one more problem just for an homework purpose or assignment. You note down this particular question. Determine the pole locations of sixth order Butterworth low pass filter with unity 3 dB cutoff frequency. Sketch the same. So very simple and straightforward. So they have already given you what is the order of the filter. Okay, you need to sketch where the pole lies, location of the poles, and what is the cutoff frequency that at 3 dB. What is the cutoff frequency that we are getting? It is unity, which means that 1 radian per second, right? Okay. Now we will move to second approximation method, that is Chebyshev filter approximation method. So once again, the main disadvantage in Butterworth filter. So when, if you observe carefully, so ideal low pass filter, I should get sharp fall down, right? This is my ideal low pass filter. Now okay, I derived an approximation method, and that is Butterworth derived an approximation method, which was something like, so I start with here, suddenly as omega increases, the response of the frequency used to fall down uh, very fast. Monotonically it decreases. So that is, there is a decrement in frequency response. The frequency response used to decrease monotonically, right? So what does it mean? What was the problem? So I am not able to get this sharp edge. What was the major problem? I am able to lose these frequencies, right? I am not able to get the frequencies at these instants. So these were missing out, which means that because of this monotonically decreasing the frequency responses as the omega increases, so as the cutoff frequency increases, I am losing lower frequency component. These are the lower frequency component, right? So these components, lower frequency components, were missing. So this was the one of the disadvantage in Butterworth filter. Now for this we got a remedy, and that is through the Chebyshev filter. I'm sorry, I made a typing error here. This is why I go with a Chebyshev filter. So where once again the Chebyshev filter, here I am trying to get more approximate, or more nearer to my ideal filter, ideal response. So here I am trying to see to that, instead of sharp or a fast monotonical decreases, is it possible to shift this decrement to the next level? So that is going to be observed in the another mathematical approximation method given by Chebyshev. So that's where we have type 1 approximation method and type 2 approximation method. Now we will see directly the mathematical expression. As I told you, this is the curve that I require. This is the curve that is I require, or that is the needed. So this is always omega, and this is always h of j omega, or h of omega magnitude value. So this for this mathematical equation, so I have a Chebyshev type 1 mathematical expression here. So this is the expression. Just note down this expression directly. So here, looking into the previous method, that is Butterworth method. So this is epsilon square and Cn square are the two more terminologies that is going to be added here, so that just to make sure that there will be a there will the sharp monotonical decrement is going to be avoided. Okay, so in turn I rewrite this equation as epsilon square Cn square of x, where x is nothing but omega divided by omega c. That's it. So now these two are the denominator terms are always called as a Chebyshev polynomial, that is the Chebyshev polynomial in passband and in stopband. So look at this. This is Cn of x. We call it as the Chebyshev polynomial, a quadratic value here. So which is going to be represented as cos of n into cos inverse of x, and passband, at the passband this value is going to be replaced with hyperbolic value cos h of n into cos h inverse of x. So we don't have derivation for this Chebyshev filter. Directly, I'll give you the value of finding the order of the filter and finding the value of the epsilon. Okay, and that is passband attenuation and stop band attenuation. In turn, the cutoff frequency. How to identify the cutoff frequency? That's it. Okay, now okay, what is the advantage here? So this is always well within the passband, but one of the important point here is, if I plot the frequency curve, definitely I could able to observe more nearer to my ideal low pass curve. But one of the very important point in this condition, in this particular problem here, I'm going to get in the pass band and in the stop band, I'm going to get a small ripples, and then a sharp edge is going to be obtained, and this is how the fall of frequency response as omega, as it reaches to cutoff frequency. So now once again uh, there will be a ripples in the stop band. So this is, we call it as pass band ripples. This we call it as pass band ripples, and here we call this as stop band ripples. Here it is called as stop band ripples. So which means that there is, if I take a effective effective pass band and stop band. So this is it. If I consider this to be 1, and this is will be 1 minus epsilon, some difference or some length difference will be created. So, what is the purpose of occurring these ripples? The main intention is go look back to the previous slide here. If you take this Cn of square, which is a polynomial, this polynomial is not independent values. It is depending upon cos of something, right? Cos of something, which is nothing but there must be a cosine waveform, or if it is 90 minus theta, then definitely it is a sinusoidal waveform. So obviously, when there exists a cos term in this polynomial, this is unavoidable for me, is it not? The ripples are unavoidable. So as I told you, either in this fashion I will be having a ripples, or either in this fashion, that is cos value, how it varies, or this is how it varies, right? So in this fashion, once again I will be having the ripples. So the is it possible to avoid the ripples? No. Only way is I can avoid the ripples at in either pass band or stop band. So that is why it is called as type 1 and type 2 approximation method. There are two equations. The type 1 method is one where the ripples occurs in the stop band. The type 2 is one where the ripples occurs in the pass band approximation method. Pass band at the pass band. Okay. So these are the two difference between type 1 and type 2. And in the lab and all, we will be using the type 1 Chebyshev approximation method. Okay. So this is one disadvantage. That's where the passband frequency response will be varying between. So you cannot say that it is exactly one, or you cannot say that it is going to be, sorry, this value is going to be 1 by 1 plus epsilon square, right? So you cannot give the assurance that the value will lie here. So this will be varying between the passband. The responses will be varying between well within this particular range. Okay. So the Chebyshev polynomial is a cosine function. So therefore, the response is not constant. The response is not constant like this. It will be varying like this. Okay. So this is the reason, because of cosine function. Okay. So because of that variation, so I will be getting this height, right? So that height is nothing but 1 minus 1 plus 1 minus 1 divided by 1 plus epsilon square. This is 1 divided, this value is 1 divided by 1 plus epsilon square. Okay, the other few points where the period of oscillations is not same, and number of ripples. Okay, very important point. So how many ripples does exist in your Chebyshev approximation method? So these ripples is entirely depending upon your filter order order of the filter. If pole increases, the ripples also increases. If poles decreases, less number of order, and obviously the ripples are also less. Okay. So this is all about the Chebyshev approximation method. About the brief theory. That's it. Okay. Now, directly, this is all about the frequency response as I explained here. Okay. So this value will be 1 divided by 1 plus epsilon square, and this height is nothing but 1 minus this value will going to give me the height. Okay. So n, which means that another very important point, if I have even number of poles and if I have odd number of poles, that's how it is going to be varied here. So look at this, n is odd, so it is going to give me a value kind of cosine wave, and if it is going to be n is even, so obviously uh, cos for all values of n, cos will be 1, so that value. So hence I'm going to get at the maximum peak value here. Else, if for n is even, so ultimately this value will be 0. So therefore it starts with in this fashion. So these two are the differences, that is the curve differences. Okay. Now observations. Okay. The one of the important observation that what we make in the type 1 approximation method, right? So that is also Butterworth was also all pole system, and Chebyshev is also all pole system. But with respect to origin, in case of Butterworth, if I plot a freehand curve wherever the pole lies, so that was giving me a circle. But in case of all pole Chebyshev type 1 approximation, it will going to give me a shape of eclipse. So this is how I am going to see the S plane, right? So this is where we will going to get where these shapes are going to be appeared. So these shapes are on the S plane. Okay, so this is for Butterworth, so this is for Chebyshev, so which will look like a ellipse. Okay, because of this there is a transition region narrower in comparison with a Butterworth approximation method. So I'm going to sharp edge. So obviously this this is exactly more exactly or more idealistically I'm going to get this output. So hence the transition is narrower. So there it was not narrowed. So there it was something like monotonically decreases. So I'm going to get a broader transition width. Okay. So when you comparison with error, so Butterworth was little more erroneous when compared to Chebyshev. Okay, so that is one of the another differences between Chebyshev filter and Butterworth filter. Okay, you can observe the another very important point here. It is for a given specification Chebyshev filter less filter order, and hence it is also called as least order approximation. The Chebyshev filter or Chebyshev approximation is also called as least order approximation method. So you mark this point, we will solve the example, we will come to know why it is called as least order approximation method. Okay. Now just go through the formulas. So these are the formula that we use. Okay, so this is passband attenuation minus 10 log 10 of 1 plus epsilon square. So as I told you, directly we'll be using the formulas to calculate. So as in Butterworth we derived this value of n. So here we don't have that for your syllabus. Directly we take the value of n to calculate. Directly we take this equation to calculate the value of n. Okay. So order of the filter n is equal to cos h inverse hyperbolic cos h inverse of delta by epsilon. What is this delta? Delta is nothing but, so which is pertaining to passband stop band frequency. Okay, divided by cos h inverse of omega s by omega p. Now this delta is given by 10 to the power of minus under the square root 10 to the power of minus zero point 0.1 as minus 1. That's what I have written here. So this is, and epsilon. So this is going to be a epsilon value under the square root 10 to the power of minus zero point 0.1 ap minus 1. So cos h inverse of omega s to the omega p. Okay. So directly we solve the examples. I hope you noted down this. You already noted this formulas. So now we'll solve the one example, and we'll we'll end up the session. Okay. Determine the low pass filter. Determine the LPF order of to meet the following specification using Chebyshev approximation method. So this is the same example that we solved for order of the filter in case of Butterworth. We already solved for this, right? So let me take up the same example and try to solve this. So where n is equal to cos of cos h inverse delta of by epsilon whole divided by cos h inverse of omega by omega s pass band to the stop band. Sorry, stop band to the pass band here. There it was pass band to the stop band. Yes, stop band to the pass band. So now you need to find out the delta value, epsilon value. What is delta here? Delta is nothing but under the square root 10 to the power of minus zero point 0.1 into as, right? Minus 1. What is as? So under the square root 10 to the power of minus zero point 0.1. The value of as is minus 2 dB, right? Stop band, sorry, stop band here it is 75. 75 minus 1. Find this value and calculate the value of epsilon. Epsilon is again under the square root 10 to the power of minus zero point 0.1 AP minus 1. What is passband attenuation? That is 0.1 into minus 2 minus 2 minus 1. So let me know the value of this these two value, delta value and epsilon value. Find out ಮಾಡಿ. What is the value of delta? See, after calculating delta value, which comes to be around 5623 and epsilon value is 0.764. Now let me put here cos h inverse of 5623 whole divided by 0.764, and this is entirely divided by cos h inverse of omega s, that is stop band frequency. Stop band frequency is minus 75, sorry, 500 pi, 5000 pi divided by passband frequency is 500 pi. Okay, solve for this and calculate the value of n. Solve this and calculate the value of n. So the value of n is somewhere else around 3.21 is approximately, I am going to take it as 4. Okay. Now this made me a very difficult for me to make you understand because in the previous example also using Butterworth we got n equal to 4 itself, right? Okay. Since it is depending on this passband and it is depending upon the lesser value of passband frequency and stop band frequency. So let me take a quickly we'll take a one more example. Okay, quickly we'll go for taking the one more example. So your first example that we what we solved in Butterworth example. Take up that. I'll just apply. I just write the figure. I'll just write the figure quickly. So this was the question where the stop band frequency was how much? Anybody can help me out? What was the passband frequency? ನಿನ್ನೆ ಮಾಡಿದ್ವಲ್ಲ, yesterday's first example. very first example. Yeah, 1000. So what about stop band? So this is pass band 1000 hertz, right? This was in terms of hertz, right? And here the attenuation, pass band attenuation was minus zero point 0.1, right? Minus zero point 0.1. And one more at 2000 hertz, right? The stop band attenuation at minus 70 dB, if I'm not wrong. Yeah. So this is h of omega magnitude in terms of dB, and this is in terms of hertz. Now, solve for this problem. Find order of the filter. Find order of the filter using Chebyshev type 1. Chebyshev type 1. So again same thing, the value of n, order of the filter, it is cos hyperbolic inverse function of delta divided by epsilon or divided by cos h inverse of omega stop band to the omega pass band. Now calculate the value of this. So before to that, so let me calculate d value, delta value. Delta is nothing but under the square root 10 to the power of minus zero point 0.1. This is stop band. What is this? This is uh, pass band. Pass band here it is zero point 0.1 again. So it's inside this zero point 0.1 minus 1. So how much you're going to get? Calculate and tell me. So this is epsilon again 10 to the power of minus zero point 0.1 into AS. AS is minus 70 minus 1. So this is equal to what? Quickly find out the value of delta and epsilon. So look here, after putting these values, we got the value of n after calculation of all delta, epsilon, and when I substitute here, then finally I'm going to get n equal to 8. So I can round it to 9, or else even I can round it back to 8 itself. So okay, let me consider 9 itself. Let me take one capacitor extra, no issues. Now, tell me what was the value for n for Butterworth approximation? It was, yeah, 15, right? For the same specification using Butterworth, for the same specification using Butterworth, we got the value of n to be 15. See here, almost 50% reduction in my order of the filter, right? Nearing, approximately nearing, right? So if I consider n equal to 8, this is approximately 50% reduction, right? So this is the advantage, and moreover I'm going to get the sharp stop. What is that? The stop, not monotonically decreasing. I'm going to get approximately more realistic or idealistic curve when as compared to the Butterworth filter. The Chebyshev filter giving me the same filter approximation. If I want to pass all the frequencies that come under less than 2000, so from 0 to less than 2000, whichever the frequency signals that appears to be, so I am trying to pass all those frequencies. Now I need to design the hardware. So to design the hardware, so I need to know how many L and C components are required. So that is what we call it as the order of the filter. And order of the filter, if I make use of the Butterworth, I am getting 15 of such poles, and here I am going to get only 8 poles. Within 8 poles, by making use of only 8 poles, I can pass all the frequencies from ranging from 0 to 2000. That is what the meaning here. Okay. So This is why it is called as Chebyshev filter. The Chebyshev filter is called as least order filter. Okay. So as order n decreases, the number of memory element also decreases. So as it decreases, then your hardware cost also reduces. So this is with this example, I think I'm able to convey you one of the important point, that why Chebyshev filter is called as a least order filter. Okay. So let me end the session here. Tomorrow's class, we'll see the transformation of the one more example if possible, and followed by the transformation of the signals, transformation of the frequency domain from LPF to HPF and HPF to LPF filter as such. So I'll design low pass filter. If I want to convert it to HPF, yes, I design LPF, I will convert it into high pass filter. If I want to design band pass filter, I will design LPF, I will convert it into band pass filter. This, the ready-made formula is available, so we'll make use of those formulas and design the filter by converting from LPF to HPF filters. Okay, so that is why we concentrate more on designing low pass filter itself. If I able to design low pass filter, if I want HPF, I convert that low pass filter into HPF by using suitable transformation techniques. Okay, anything is possible if you could able to design a one small low pass filter design. Okay, okay then. Let me stop here for the day, and let me continue the session in the next class.